Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous video lecture, I have discussed about unit number 3, wave mechanics. In this video, I am going to discuss about unit number 4, semiconductor physics. So let's get started. The content of this lecture video is as follows. I will discuss about free electron theory followed by Kronig-Penney model. Free electron theory. The free electron theory of metals aims to explain the structure and properties of solids through their electronic structure. The electron theory is applicable to all solids, that is both metals and non-metals. It explains the electrical, thermal, and magnetic properties of solids, etc. The theory has been developed in three main stages. So first is the classical free electron theory. Drude and Lorentz proposed this theory in 1900. According to this theory, the metals containing that free electrons obey the laws of classical mechanics. The treatment of a metal as containing a gas of electrons completely free to move within it. The theory describe and correlate the electrical and thermal properties of metals. Later, quantum mechanics became the basis of the theory of most of the general properties of simple metals such as sodium with 1 free electron per atom, magnesium with 2 and aluminum with 3. Traditional metals such as iron have partially filled electronic d states and are not treated by the free electron model. The valence electrons are involved in electrical conduction in metals and alloys. Valence electrons become free in solids and move about randomly within the solids in the same way molecules in a gas confined to a container. Hence, they are known as free electrons. Neglecting the electron-electron interaction and the electron-ion interaction, it is similar to situation that electrons undergo periodic collision with ions in the lattice. So this was about classical free electron theory. Now let's see the quantum free electron theory. Sommerfeld in 1928 applied the principles of quantum mechanics to classical free electron theory. According to classical theory, the free electrons in a metal have random motions with equal probability in all directions. But according to quantum theory, the free electrons occupy different energy levels, up to Fermi level at 0 degree Kelvin. So they possess different energies and hence they possess different velocities. The different velocities of these free electrons of a metal can be seen in velocity space. So let's see some assumptions. According to the quantum free electron theory, the assumptions are as follows. The energies of free electrons are quantized. The distribution of electrons is as per the Pauli's exclusion principle. Electrons travel under constant potential and confined to the boundaries of metal. All the attractive and repulsive forces are neglected. Electrons on this energy level are also called fermions and obey Pauli's exclusion principle. Each energy level can accommodate at most 2 electrons. This highest occupied energy level by the electron at 0 Kelvin is called Fermi Energy level. At 0 Kelvin energy levels, below the Fermi level are completely filled and above Fermi level all the energy levels are empty. If the temperature increases above 0 Kelvin, the probability occupation of electrons at that level is half. That particular energy of that level is called Fermi energy. The value of Fermi energy in metal is about 5 electron volts. According to the quantum free electron theory, the motion of free electron in metals is shown in this animated figure as per Drude model. Drude model, the electrons shown in red constantly bounce between heavier stationary crystal ions shown in blue. So this is all about the classical and quantum free electron theory, which is very basic information about that. Now let's see the definitions and some relations. First of all, drift velocity. The drift velocity is defined as the average velocity acquired by the free electrons of a metal in a particular direction by the application of electric field. Relaxation time, second definition, it is defined as the time taken by the free electrons to reach its equilibrium position from the disturbed position in the presence of electric field. Next one is collision time. Collision time defined as the average time taken by the free electrons between two successive collisions. Current density. Current density is defined as the magnitude of current passing through unit area. So capital J is equal to capital I upon capital A. So J is a current density, I is a current, and capital A is the area. So this equation can be written as I is equal to integration of J into ds. Now let's see the expression for relaxation time tau r. When the metal is subjected to an external electric field, the electrons move opposite to the applied field. After removal of electric field, the drift velocity decays exponentially with the help of the equation Vd is equal to V naught exponential of minus tau upon tau r, where V naught is the initial velocity of an electron before application of electric field and tau r is the relaxation time. If tau is equal to tau r, then Vd is equal to V naught exponential of minus 1. Or this equation we can write Vd is equal to V naught upon E. Thus, the relaxation time may be stated as the time taken for the drift velocity to decay to 1 upon E of its original initial value. Now let's see the mean free path denoted by lambda. Free electrons in a metal are continuously moving in all directions and with various speeds. They frequently collide with one another. Therefore, they move in straight line with constant speeds between two successive collisions. The distance traveled by the electron between two successive collisions is called as free path, and their mean is called the mean free path. The average distance traveled by the electron between two successive collisions is called mean free path, or the mean free path is the average distance traveled by an electron between two successive collisions with other free electrons. Therefore, lambda can be written as lambda is equal to c bar tau, where c bar is the mean square velocity of electron, which can be written as c bar is equal to under root of 3kb T upon m, where kb is the Boltzmann constant, T is the temperature, and m is a mass of an electron. Now let's see the success of free electron theory. The free electron theory was successful in explaining properties of metals as below. The theory successfully explains Ohm's law. Electrical conductivity of metal, it explains electrical conductivities of metals, that is the electrical conductivity, that is sigma is equal to Ne mu, where N is the electron density, E is a charge on electron, and mu is the mobility of electrons. The thermal conductivity, it explains thermal conductivity of metals at lower temperatures. Thermal conductivity of metals, that is capital K, is equal to Kb N V lambda divided by 2, where Kb is the Boltzmann's constant. The free electron theory also explains the relation between electrical and thermal conductivity, which is called as Widman-Franz law. The Widman-Franz law states that the ratio of the thermal conductivity and the electrical conductivity of metal is proportional to the temperature. It can be shown that capital L is equal to small k upon sigma T, where k is a Boltzmann constant, sigma is a conductivity, and capital T is a temperature, is equal to 2.44 times 10 raised to minus 8 watt-ohm per Kelvin square. This number is called as Lorentz number. Even though free electron theory successfully explained the thermal and electrical properties, there are several limitations of free electron theory. So let's see these limitations. According to the theory, conductivity of metals is proportional to electron concentration. If this is always true, divalent cadmium, zinc, etc., and trivalent aluminum, etc., atoms should have more electrical conductivity than monovalent atoms like copper, silver, etc. This model cannot explain the classifications of solids into conductors, semiconductors, and insulators. The theoretical values of mean free path of electrons as calculated from this theory do not agree with the experimental values. The theoretical values of specific heat and electronic specific heat as calculated from this theory do not agree with experimental values. Some metals such as zinc have positive values of Hall effect. This theory could not explain why zinc and other metals have positive value of Hall coefficient. Widman-Franz law deviates at low temperature. So these are the limitations of free electron theory. So this is all about the free electron theory. Now let's see what is Kronig-Penney model. To overcome the limitations of free electron theory, the periodic potentials due to the positive ions in a metal have been considered, which is explained with the help of Kronig-Penney model. The Kronig-Penney model, named after Ralph Kronig and William Penney, is a simple idealized quantum mechanical system that consists of a finite periodic array of rectangular potential barriers. The potential function is approximated by a rectangular potential as shown in this figure. The Kronig-Penney model is a strongly simplified one-dimensional quantum mechanical model of a crystal. Despite of the simplifications, the electronic band structure obtained from this model shares many features with band structures that result from more sophisticated models. Kronig-Penney model says when an electron moves through a lattice of positive ions, it experiences varying potentials. The potential of an electron at the positive ion site is zero, and it is maximum in between two ions as shown in this diagram. Kronig and Penney suggested a simplified model where atoms are represented as one-dimensional infinite row of rectangular potential well, which is separated by barriers of width small b. Each well has width b and depth v0. The interatomic spacing is represented as a small a. The period of potential is a plus b, which is clearly shown in this diagram. The animation of Kronig-Penney model is shown in figure number 3. This is the band structure of the Kronig-Penney model. As you gradually turn on the potential, the black rectangles, and see the colored bands begin to split. The horizontal axis is in k space, which is not real. So the spacing of the barriers and the veils isn't meaningful in an absolute sense and is merely for decoration. The height of the barriers in terms of the vertical energy scale is correct, as well as the relative sizing of the barriers and the veils. It is not easy to solve Schrödinger's equation with these potentials. So Kronig and Penney approximated these potentials inside the crystal to the shape of rectangular steps as shown in this figure number 4. This model is called Kronig-Penney model of potentials. In order to find the allowed energies of electrons in solids, we have to apply Schrödinger's wave equation for an electron in a crystal lattice. By solving this Schrödinger's wave equation using Bloch theorem, we get energy capital E versus momentum small k as shown in this diagram. In Kronig-Penney model, the energies of electrons can be known by solving Schrödinger's wave equation in such a lattice. The Schrödinger's time-independent wave equation for the motion of an electron along x direction is given by d square psi by dx square plus 2m upon h bar square in bracket capital E minus capital V of x bracket complete of psi is equal to 0. Let's say this is equation number 1. The energies and wave functions of the electrons associated with this model can be calculated by solving time-independent one-dimensional Schrödinger's wave equation for the two regions 1 and 2 as shown in figure number 4. The Schrödinger's equations are first for the region first at 0 is less than x is less than small a, the potential energy capital V is equal to 0. Therefore, d square psi by dx square plus 2m upon h bar square into capital E into psi is equal to 0. Let's say this is equation number 2. Now for the region 2 at minus b is less than x is less than 0, potential energy capital V is equal to V naught. Therefore, the above equation can be written as d square psi by dx square plus 2m upon h bar square in square bracket capital E minus V naught bracket complete into psi is equal to 0. Let's say this is equation number 3. We define two real quantities, let's say alpha and beta, such as alpha square is equal to 2me upon h bar square. Let's say this is equation number 4. And beta square is equal to 2m upon h bar square in bracket V naught minus capital E. Let's say this is equation number 5. Hence equation number 2 and equation number 3 can be written as, therefore d square psi by dx square plus alpha square into psi is equal to 0 for 0 is less than x and x is less than small a. Let's say this is equation number 6. And d square psi by dx square minus beta square psi is equal to 0 for minus b is less than x is less than 0. Let's say this is equation number 7. According to Bloch theorem, the wave function solution of the Schrödinger's equation when the potential is periodic and to make sure the function u of x is also continuous and smooth. So that can be written as psi of x is equal to exponential of ikx into small u of x. Let's say this equation number 8. In this equation, u of x is a periodic function which satisfies u of x plus small a is equal to u of x. Using Bloch theorem and all the boundary conditions for the continuity of the wave function, the solution of Schrödinger's wave equation obtained as, in first bracket, small m capital V naught AB upon h bar square into bracket sine of alpha A upon alpha A bracket complete plus cos alpha A is equal to cos KA. Let's say this is equation number 9, where alpha is equal to under root of 2me upon h bar square. The energy capital E is restricted to lie within certain ranges. Capital P into bracket sine of alpha into A divided by alpha A bracket complete plus cos alpha A is equal to cos Ka. Let's say this is equation number 10, where capital P is equal to small m capital V naught AB upon h bar square. So we just simplified the equation number 9. This equation number 10 shows the relation between the energy through alpha and the wave vector small k. The above equation provides allowed solutions to the Schrödinger's equation. Due to cosine term, the right hand side varies between +1 and -1. And so left hand side is also allowed to vary between these two values. Thus, only certain values of alpha are possible, as alpha is equal to under root of 2m capital E upon h bar square. The energy capital E is restricted to lie within the certain ranges. Therefore, the relation between energy capital E and the wave number small k is a periodic. The motion of free electron is interrupted at certain values of small k, as shown by the broken curves in this diagram, that is the figure number 5. The plot also shows discontinuities in energy of electron at small k is equal to plus minus pi upon a, plus minus 2 pi upon a, plus minus 3 pi upon a. These gaps corresponds to energy bands inside the solids. Thus, the energy level of electron in crystal lattice is discrete. The dotted line representing the motion of a free electrons. As electron is moving in periodic potential, it appears that there are gaps which open in energy spectrum at an integer of k into a upon pi. The gaps corresponds to energy bands inside the solids. Thus, the energy level of an electron in crystal lattice is discrete. This is all about free electron theory and Kronig-Penney model. In next lecture video, I will discuss about band theory of solids. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's classroom channel to get the notifications about my upcoming videos. Thank you.